You know, the single most damaging thing you can do to a C175 engine isn't botching a torque spec or completely missing a sensor calibration. No, it's actually much simpler and much worse. It's cranking it dry. If you do a dry start, you're going to score those bearing surfaces in a matter of seconds. And the brutal truth? That damage literally never fully heals. Ever. To combat this, CAT engineers built in specific pre-lube strategies just to guarantee that never, ever happens. So in today's explainer, we're going to break down exactly how these pre-lube systems actually work, how you can manually override them when things go sideways, and how the specific application of the engine totally dictates its maintenance schedule. So here's our logical roadmap for today. We'll start with how fluid control works in pre-lube systems, then we'll check out the emergency override panel, move into application-specific maintenance, and wrap up with testing insulation health. Let's dive right in. All right, Section 1, pre-lube systems, specifically continuous versus automotive. You see, before a massive engine like the C75 even thinks about cranking over, it absolutely needs a protective oil film. Without it, you get catastrophic metal-to-metal contact on the internal bearings, and the C175 actually achieves this protection through two totally distinct automated systems. First up, we have the continuous pre-lube system. This is used pretty much exclusively for standby or critical applications. And I mean continuous. It literally never stops running. It pumps oil 24/7. Now, why do this? Well, you're basically accepting the trade-off of constant pump wear to guarantee instant readiness. On the flip side, we've got the automotive pre-lube system, and this is for prime power. It stays completely quiet until a planned start, runs just long enough to sense adequate pressure, and then it allows cranking. So here, you're trading a few seconds of delay to save on pump wear over the long haul. Looking at this setup, the documentation is super clear. A relatively small population of engines, the ones strictly for emergency power, ship with that continuous pre-lube pump. But standard prime engines, the vast majority of them use the automotive system. That gives the engine just enough time to build pressure up to roughly 7 kilopascals or about 1 psi right before the starter actually engages. If you're sitting there wondering why we even need two totally different setups, just think of an ambulance versus a delivery truck. It's a great analogy. The ambulance keeps its engine idling and ready to go at all times, right? Because when a life safety call comes in, there are literally 0 seconds to spare. That is your continuous pre-lube. The delivery truck, though, starts its engine fresh each morning on a nice, predictable schedule. It takes a few extra seconds to warm up properly before hitting the road. That's your automotive pre-lube. So you see, it's not just some random engineering preference. It's a direct consequence of the application's required response time. Okay, let's pause for a quick real-world scenario. Imagine you're managing a facility. Your standby generator fails its mandatory 10-second start window during a routine test. Let's say it takes 14 seconds instead. What's the very first system you'd suspect? I mean, usually most people are going to guess the starter motor or maybe, degraded batteries. Well, actually, the real answer is the continuous pre-lube system and its pressure sensor. Think about it. A standby application is supposed to have oil already circulating and ready at all times. So a slow start points directly at a pre-lube fault. The engine's ECM literally will not allow the crank to happen until pressure is confirmed. So if it's taking too long, it's highly likely your pre-lube pump has failed, not your starter. Moving right along to Section 2, the emergency override panel and the anatomy of control. Because let's face it, sometimes even the smartest automated logic in the world needs a human operator to step in and take direct control. And that is exactly where this override panel comes into play. What's really fascinating here is seeing all 5 of these distinct override switches clustered together. Each one gives a technician the ultimate authority to bypass protective logic. We've got crank override for directly engaging the starters, engine protection override, manual pre-lube, low idle select for controlled warm-ups, and rapid start/stop to toggle high-speed sequencing. Make no mistake, every single one of these switches dramatically changes the engine's default behavior. Now, we really need to slow down for a second and emphasize the engine protection override. When you flip this switch, you are telling the engine's ECM to completely ignore all shutdown alarms. This is literally a run-to-destruction switch. You are willingly sacrificing the engine to the power gods. Because in that moment, losing electricity poses a much greater immediate danger than internally melting down a generator. So yeah, it is never, ever a shortcut just to bypass a nuisance alarm. But for your normal routine service, the manual pre-lube switch is going to be your absolute best friend. Seriously, after an oil change, or honestly any maintenance where you've drained the lubrication system, never just assume the automated cycle will handle it perfectly. You use this switch to manually force the pump on, you visually confirm that you actually have proper oil pressure, and only then do you allow a normal start cycle to kick off. It is absolutely essential as your ultimate safety check. All right, on to Section 3, application-specific maintenance. Let's talk about tailoring the schedule. We really need to look at how these two very distinct operational modes, standby versus prime, completely alter the required service intervals for the engine. Because, spoiler alert, you simply cannot maintain them the exact same way. Since standby and prime power applications accumulate wear in totally different ways, their service schedules have to run on entirely separate tracks. Just look at the breakdown. A standby engine, it might sit idle for weeks and then bam, jump to full load instantly. That means it has very low hours but requires incredibly high readiness. Meanwhile, a prime engine is just churning away, running continuously for thousands of hours under steady loads. Because of that huge difference, the frequency of oil sampling and your overall service needs have to be tailored exactly to what the engine is actually doing day in and day out. And the maintenance manual is incredibly strict about this stuff. For example, it strictly requires you to change the engine oil and filters every 1,000 service hours. But you also have to thoroughly inspect the pre-lube pump itself every 7,000 service hours. Sticking religiously to these distinct intervals is exactly what ensures that your pump won't fail you when you desperately need that 10-second emergency start. Okay, bringing us to Section 4, testing insulation health using the Megger test. We're stepping away from fluid dynamics and electronic control for a minute, and we're going to look at testing the overall electrical health of the generator itself, specifically the stator windings. To really grasp why a Megger test is so vital, especially for those standby units, think of a damp sponge versus a bone-dry sponge. If you touch a low-voltage circuit to a damp sponge, it conducts a small trickle of electricity pretty easily, right? But a completely dry sponge, it blocks that electricity entirely. Well, when generators just sit idle, especially if you're in a humid or coastal environment, the stator winding insulation acts exactly like that sponge. It absorbs moisture right out of the air, and this moisture creates an unwanted conductive path. So a Megger test basically pushes voltage through the insulation to catch exactly this kind of slow, reversible problem before it blows up into a massive winding failure. So let's put your knowledge to the test. Imagine you hook up your diagnostic tools. You run a Megger test on a generator that's been sitting cold for a month, and your tool reads exactly 1.5 megohms of resistance. You have to ask yourself, does this reading pass or does it fail? Well, if you guessed fail, you're right. A reading of 1.5 megaohms is a strict, undeniable failure. On these systems, anything under 2.0 megaohms indicates some serious, dangerous moisture or dirt contamination, and it mandates an immediate dry-out procedure. That means you literally have to actively heat the windings, whether that's via built-in space heaters or a forced air oven, to bake that moisture completely out of the insulation. You keep at it until your resistance climbs steadily back up above that 2.0 megaohms safety threshold. I'll leave you guys with this slightly provocative thought. Before you go and diagnose your next slow start, or condemn a starter motor, or start ripping apart an electrical panel, ask yourself, are you treating the engine exactly as its specific application demands? Really think about it. Are you working on an ambulance or a delivery truck? Truly understanding that difference completely changes everything about how you troubleshoot. Thanks for joining me on this explainer, and hey, keep learning.